Well, I'm really glad to welcome Carl K9LA back to present to us again and give us an update on solar cycle 25. It's very timely. We just heard a report from Lloyd and 9LB about all the expeditions are going on and the success that everyone is having with them, not only in our club, but worldwide. And a lot of that has to do with the solar cycle. And if you go back in our YouTube archives, you'll find a presentation by a NOAA scientist a few years ago that he and NOAA had predicted that this would be a below average solar cycle. And we're going to hear from Carl that perhaps, like many weather forecasts, that might not quite be as accurate as it could be. So with that, Carl, take it away.
Okay. Thank you, Kevin, and hello to the Madison DX Club. I'm Carl, K9LA in Fort Wayne, Indiana. We're on Eastern Time, even though we're pretty far west. We're still on Eastern Time here in Indiana. And yes, the bands have been very good, and lots of de-expeditions and lots of people to work, so that's great. Let me share my screen. Let's see, there's the Madison DX. Share it and go full screen. Well, I think it must be on, I bet.
There we go.
There we go. Yeah, there it just showed up on my screen that we're on. So the title is an update on cycle 25. So that's what I'll mostly be talking about. But there's some related topics. I had a question from Gary W9XT in an email this morning, and I hopefully added the answer to that. So we'll see what happens. And the little picture on the left there, cycle 25 is very awake. So get on the air and have some fun. And I enjoyed Lloyd, when you had a real-time picture there. It was comforting to see a very nice wireless station there. Yeah, right. Okay. So what we're going to talk about is it's always good to talk about history, the previous 24 cycles. Talk about some predictions that have been made for cycle 25. Then we'll get to the latest data, and that's going to, trump any predictions, what cycle 25 is really doing. So it also gives us an idea where it's kind of headed to, the real data. I got some slides on the outlook for 160 and 6 meters, and some miscellaneous stuff if we get to it. So I've shown this quite a bit, but I think it's always good to remind ourselves of what's happened in the past. This is all the previous 24 solar cycles. That's what the Excel graph shows, is the maximum smooth sunspot number of each of the previous 24 cycles. Cycle 1 began in 1755, so that was before my time for sure. I'm sure you've heard of the Maunder minimum. That was when there were few sunspots. That was before cycle 1. It was 1645 to 1715. And what really stands out in the plot of the maximum smooth sunspot number for each cycle is we've gone through 3 periods of big solar cycles, like cycles 1, 2, 3, 4, cycles 8 through 11, and cycles 17 through 23 were kind of big. That also says we've gone through 2 periods of small solar cycles. 5, 6, and 7, they were small. 12, 13, 14, 15, 16 were small. And 24 was small too. In fact, it was the smallest in our lifetimes, unless you're really, really, really old. And it was the fourth smallest in recorded history. So that's how small it was. Cycle 6 was the smallest. And so that kind of says that we appear to be in a 3rd period of small solar cycles. Now we have to watch that because we have 270 years of sunspot data, okay? But sunspot cycles have probably gone on for hundreds, thousands, and millions of years on the sun. So we have a pretty small sample size. So don't be surprised by what could happen, I guess. But what the pattern suggests right now is that cycle 24 ushered us into a period of small solar cycles. And that kind of leads to, well, is cycle 25 going to get us out of this period? Or is it going to do something rather interesting? I've highlighted some other solar cycles. Cycle 24, of course, is small. Cycle 23 is an average cycle. If we get up to an average cycle, we'll be very happy, I think. Cycle 21 was a moderate cycle that peaked in 1979. And of course, there's 19, the largest in recorded history. One of the questions that people ask is, will cycle 25 have one peak or two peaks? Cycle 23 had two peaks. Cycle 24 had two peaks. And there's some data. The green dots are the total number of sunspots. The blue is the sunspots that occurred in the northern hemisphere of the sun. Orange is the number of sunspots that occurred in the southern hemisphere. And you can see why we had two peaks in cycle 24. At the start, the northern hemisphere was active and the southern hemisphere wasn't that active. But then that switched later on. The southern hemisphere got very active and the northern hemisphere kind of calmed down. That gave us the two peaks. So what's cycle 25 going to do? Well, so far, pretty much the two solar hemispheres are working together. But you got to watch, there's been a downturn in the southern hemisphere, so we'll have to wait and see what happens. Maybe that's just a temporary lull and they'll keep tracking. Now, what you can also see in the green dots, the total number of sunspots is cycle 25 has surpassed cycle 25 already. So we'll just have to wait and see how big cycle 25 will get. Will it get up to an average cycle? We'll talk about that in a little bit. Predictions for a solar cycle. Here's a little visual picture of the predictions for cycle 24, the previous solar cycle. As you can see, there were quite a few. There were over 55. And they varied from a very small solar cycle on the left to a very big solar cycle on the right. Why are there so many predictions? Well, we just don't fully understand the solar cycle process. We have the general idea, but just not all the details. So that results in people making predictions based on different methods. One of the most common is the precursor method, where something before cycle 24 starts tells us what cycle 24 is going to look like. Now, of course, somebody's going to be right when you have that wide of a range of solar cycle predictions. And I'm not sure they're right for the right reason, but that's for discussion for another day. So what did we learn from cycle 24? Well, here's a little picture of the number of predictions for cycle 25. That only shows 35, but I'm aware of about 55 now, or even greater. So we didn't learn enough. Still, the details of the solar cycle process are still elusive to us. Now, for 25, NOAA and NASA predicted a small cycle, about the size of 24. And I think a lot of that had to do with the history of solar cycles, and we appear to be in a third period of small solar cycles. Dr. Scott McIntosh at the National Center for Atmospheric Research in Colorado and his colleagues predicted a big cycle. So what about that prediction for a big cycle by Dr. McIntosh? Well, they made that prediction of June of 2020, and it really went against the NOAA NASA prediction. Dr. McIntosh and his colleagues have received lots of publicity because of this prediction. Dr. McIntosh has given many updates of their cycle 25 prediction to the front range 6 meter group. In fact, he's going to be on their group next December 13th. So I encourage everyone to go watch that. Dr. McIntosh talks about a lot about the physics of the sun. And that's pretty fascinating stuff when he gets into it. And he's a good presenter too. So if this prediction was to come true, it would be similar to cycles 21 and 22, which were moderately big. Excellent propagation on the higher bands, higher HF bands, 15, 12, and 10, and lots of worldwide 6 meter propagation via the F2 region around solar maximum. Just think if we would have had rigs with 6 meters back in around 1979 and also the peak of 22 in 1989. Wow, people would have had lots of fun. But, and that's a big but, they revised their prediction. In August 2021, Dr. McIntosh and colleagues downsized their predictions to slightly above an average cycle. And what happened is something that they expected to occur did not occur till much later. And that was what they call the terminator event for cycle 24. It didn't end as soon as they thought it would. And that led them to, at least initially, that led them to predict a big cycle. But when that terminator event went about a year later than what they thought, that means they had to reduce their prediction. So their prediction now is similar to cycle 25, similar to 23. If you remember back, cycle 23 had peaked at around 2000. It had 2 peaks. The second peak was higher. We still had lots of propagation in the higher HF bands, and we had some decent worldwide propagation via the F2 region on 6. And I'm sure what helped is more rigs had 6 meters. And like I said earlier, we'll gladly take a cycle similar to 23 over another 24. So latest data, here's the real stuff here. The thick red line is the progress of cycle 25. We have 41 months of smooth sunspot number data since solar minimum in December 2019. So we're pretty far into cycle 25, no doubt about it. Also plotted are 4 other solar cycles. The green one was cycle 24. A small cycle. The orange is cycle 23, which remember I said it was pretty much the average cycle of all 24. Cycle 21 was moderately big in blue. And of course, cycle 19 in purple, largest in recorded history. So right now, cycle 25 is doing a bit better than the small cycle 24. But I have to say we're kind of running out of time. Perhaps it will get to an average cycle. Just in early September, 2 solar scientists, Upton and Hathaway, predicted that cycle 25 is going to hit a maximum of about 134, plus or minus 8, little error bounds there. So that means it's going to go up a little bit more. It may not get to a cycle 23 average type cycle, but all we can do is really, wait and see, because real data is going to trump any predictions. So what's propagation doing right now? Well, we're out of the F2 region summer slump. What is that? Well, in the northern hemisphere, lower daytime F2 region muffs occur in the summer than in the fall and winter. So we're in November, and you can see by that Excel chart that what does the MUF do, for example, on a K9LA to Germany? The summer months, the MUF's only down around 20 megahertz, which says, okay, 15 meters is probably kind of iffy. But then as we move into the fall and winter months, you can see what the MUF does. We're kind of around the orange curve, which is a smooth sunspot number of about 140. We're kind of close to that. You can see that the MUFs is over 10 meters. So what causes this trend is a change in the composition of the atmosphere. And it all has to do with atomic oxygen and molecular nitrogen. Atomic oxygen is conducive to F2 region electron production. Molecular nitrogen is conducive to F2 region electron loss. So in the summer, we have a lower O to N2 ratio. In the winter, it's higher, meaning oxygen is much more than the molecular nitrogen. So, of course, in the summertime, you can watch for sporadic E. We didn't have much of a sporadic E season, and that's kind of raised questions. What's the issue here? Has the pattern shifted in different places over Earth? That's something that probably needs to be studied some more. And of course, being in November, the major ES season is over. We'll probably see a little spike in December. That's also been historically a good month for sporadic E. Not as good as summer, but it sure helps to have something. So I talked about smooth sunspot numbers, and why do we use smooth sunspot numbers? Well, here's cycle 23, and the red data is the daily sunspot number, okay? And you can see it's very spiky. It's kind of hard to tell what a solar cycle is doing, and you could probably imagine that it might be tough to predict propagation if the daily sunspot number is going up and down so much. So the next logical thing to do is take the month's worth of data and calculate the average or the mean. So that's what the blue is. That's the monthly mean sunspot number for cycle 23. You can see that it's still spiky, but some trends of the solar cycle are coming out. That looks like there's a gap around 2001, which means maybe cycle 23 had 2 peaks. So if we do some further averaging, in other words, take the monthly means and do a running average of 12 of them, we get that green curve, which is, well, very smooth. I guess that's why it's called a smooth sunspot number. And it's pretty obvious to see what the cycle did. There was 2 peaks and there was a gap in between. If you plotted 10.7 centimeter solar flux, you'd see similar results. Daily flux would be very spiky. Monthly mean would be less spiky, but the smooth solar flux would be nice and smooth, and you can tell a lot about the solar cycle. Now, smooth values are used for 2 reasons. One is that's the best way to see what a solar cycle is doing, and that's the official number that goes in the books, the maximum smooth sunspot number. The smooth sunspot number is also the best correlation to what the ionosphere is doing, so that affects our propagation predictions. And I can only stress that we don't have daily predictions. And a great example is just the month of October, last month. The orange curve is the daily sunspot number for the month of October 23. You can see it started out as around 150 in the early part of October. And then by the time we got to the end of October, it was around 50. So the daily sunspot number took a dramatic decrease. But look at the blue curve. That's the daily maximum usable frequency over the Boulder ionoson for a 3,000 kilometer path, if Boulder is the midpoint. And you can see it remained pretty much constant throughout the whole month. So what that means is plugging in today's sunspot number may not give you an accurate picture of what propagation is doing today. That's because our predictions are statistical in nature over a month's time frame using a smooth sunspot number input. Statistical, what we get out of a propagation prediction is a median value of the MUF and a median value of the signal strength. Median implies a 50% probability. So that means the median has a distribution about it. On any given day of the month, the MUF and the signal strength could be a little bit higher, a little bit lower than the median. And that's our understanding of the correlation between sunspots and the ionosphere. Okay, outlook for 160 and 6. I think there's a general consensus that top band and 80 meters to a lesser extent isn't as good as it used to be. I certainly believe that, but you got to watch that because my memory only focuses on the good times. When we moved back north to Fort Wayne in 1988, the solar min after cycle 22, I remember strong signals from Europe on 160, and I just don't hear them anymore. So I would kind of have to agree. So what's the problem? Well, there are two issues we can think about. One is the increase in man-made noise due to all the electrical devices in our lives. Or what about climate change? If there's more CO2 in the atmosphere, does that impact stuff? So let's take a quick, a more detailed look at both of those. Increase in man-made noise. That chart, it plots data from the International Telecommunication Union document, the ITU document, radio noise. And it's man-made noise in a 500 hertz bandwidth. It's versus frequency and versus what kind of noise area you live in. Do you live in a quiet rural, a residential, or industrial? Just to point out some data on 160 meters in a CW bandwidth, that's the 500 hertz, the man-made noise level in a residential area using a short monopole is around S8. That's not very good. You'd really struggle to work a lot of stuff on 160 unless you employed a receive type antenna that has directivity. On 80 meters in that residential area, the noise is probably about S6. And by the time we make it up to 20 meters, it's down to S2. So, you know, as you go higher in frequency, the man-made noise reduces. And pretty much you should be able to hear very good on 10 meters. Now, that was 1970 data. Okay. So what about recent data? Well, you can see the citation below in April of 2019. Measurements were made in the Netherlands in rural, residential, and industrial areas. And what they found is the noise in a residential area has increased by about 9 dB on 160 meters and by about 4 dB on 20. Now that's a big issue for 160. That means the noise would be over S9 nowadays with all those electrical devices. It's not as bad as if you live in a rural area. It only increased by about 6 dB on 160 and about 1 dB on 20. So if you live in a rural area, it may not be as bad as living in a residential area. Yeah, noise is a big factor on man-made noise is a big factor on the lower bands, no doubt about it. And it looks like that could be part of the problem that 160 just isn't as good as it used to be. What about climate change? Well, there's a 2008 research paper that simulated the change in the ionosphere due to carbon dioxide increasing from 365 parts per million by volume at 30 kilometers in 2000 to 730 parts per million by volume in 2100. Now that increase doubled, basically CO2 parts per million doubled, and that was projected by the IPCC in 2007. So what they did is looked at what happened to the electron density in the lower region, E region. Well, they also looked at the F region too, but since we're talking about 11680, we're looking at the lower E region because that's where absorption occurs at night. And what happened in over the 100 years, the electron density increased by about 20%, which means about 2% in a decade, 6% in 3 decades. Now, the amount of absorption is proportional to the electron density, so 2% more absorption over a decade, 6% more absorption in 3 decades. That doesn't sound like much, but maybe there could be more done to better understand this. So I think between man-made noise and climate change, I think man-made noise trumps climate change right now. Now, I don't know how accurate the doubling of the CO2 is. Again, that was a projection by the IPCC. So if it's gone up more than what they say, then that could be more of a problem. Or if it hasn't gone up as much, then it probably isn't too much of a problem. What about 6 meters? Well, you got to remember the maximum of cycle 24 was a smooth sunspot number of 116, and we did have some 6 meter F2 propagation. Cycle 25 is above a smooth sunspot number of 125, so it's bigger than cycle 24. It may go a little bit higher too. So we should expect some 6 meter F2 propagation. Don't confuse that with transequatorial propagation that was mentioned in the 825R comments earlier. Although transequatorial propagation does involve the F2 region, it's not the same mechanism as normal F2 propagation. So most likely, we're going to have 6 meter F2 propagation in the fall and winter months. Remember that curve about how the atmosphere changes and gives us better, higher MUFs in the fall and winter months. And most likely the paths will be on the paths that stay at low latitudes. In other words, they stay close to the robust equatorial ionosphere, which is has the highest electron densities in the world. The middle latitudes have, middle northern latitudes, middle southern latitudes have less ionization. And of course, the higher latitudes, both north and south, have even less ionization. So if the path stays at the low latitudes, then gives you a much better chance of 6 meter. Here's some miscellaneous stuff. The FT8 Advantage. This chart on the left comes from the WSJT documentation. It shows the weak signal to noise limits in a 2500 hertz bandwidth for all those different modes. And you can see that where FT8 is, it's an improvement over CW and especially over sideband. Whisper is the best. But Whisper is the slowest of the digital modes for completing a QSO. And that's how, the farther down you can detect into the noise, the slower the data transfer is. Now, the question that Gary, W9XT, had is, what advantage does that have in terms of the MUF? And that's a good question. I'm able to kind of answer that because the propagation prediction program, VOACAP, has an above the MUF algorithm in it. In other words, it doesn't assume propagation quits if you're operating a little bit above the MUF. The MUF is for pure refraction. VOACAP calculates how many dB of additional loss may occur due to scatter that completes the QSO. So that means the signal to noise advantage of the digital modes translates to being able to operate at frequencies higher than the MUF, the MUF. So here's what that above the MUF loss looks like in VOACAP. The horizontal axis is the operating frequency minus the what the MUF is, and the vertical axis is how much loss. If you're operating at the MUF, then there's 0 dB additional loss. If you're operating at, well, let's say 5 megahertz above the MUF, then it's kind of around 50 dB of additional loss. That's getting kind of big. But you got to remember now on 6 meters, we can make some pretty big antennas. The noise is low, so you might be able to do that. And just eyeballing the above plot and looking at that last slide, the signal to noise limits in the 2500 hertz bandwidth kind of suggests that the more robust digital modes may allow you to operate up to 4 megahertz higher than what the MUF is doing. Now that's a estimate, so don't think that that's cast in concrete, but that's what it suggests. Something I like to do in the morning is just look at prop.kc2g.com. And what that does is it shows the MUF over the worldwide ionosons. So those are the dots with the numbers in them. Of course, the MUF is for a path with the ionoson at the midpoint of a 3,000 kilometer path. It's updated every 15 minutes because that's pretty much the cadence for most of the ionosons in the world. They report every 15 minutes. So that's pretty much real time. And this data was from Friday at 9 a.m. Eastern time. And you can see that the MUFs were in the 30s on the east coast of the US and also in Europe. So that certainly suggested 10 meters should have been open from the NA east coast to Europe, and indeed it was. So it's a good thing to look at to kind of get an idea what's going on. And of course, as the day goes on, those MUFs in the daylight area will, move west and eventually hit Japan and other areas out in the Pacific. And you can see that gives you kind of a good picture. It'd be nice to draw a great circle pass on this map, but that's not available. Okay, couple things. I'm going to go over disturbances to propagation. There are 3 types of disturbances: geomagnetic storms, solar radiation storms, and radio blackouts. So what's a geomagnetic storm? Well, that's when there's a coronal mass ejection, a CME on the sun, or a coronal hole from the sun. They have to be Earth directed, of course. And what that can do is elevate the K index. So when the K index, which is a 3-hour index telling us how active the Earth's magnetic field is, K goes from 0 to 9, it's logarithmic. So when the K index becomes elevated, that could have a detrimental effect on the F2 region. In other words, the MUFs go lower. And that's what that second bullet, CME or a coronal hole, can reduce the high latitude MUFs. And there's an example. Now this is from to show things can really get screwed up even at the lower latitudes. That's the MUF, the blue curve on top is the MUF over ionoson in Peru. You can see when on the Later in the day on August 5th, when the K index spiked up to 5 and 6, what happened? The MUF dropped quite significantly, but it did recover the next day. Now, a spike in the K index can also give a short-term enhancement at low and middle latitudes. And on the bottom there's Eglin Air Force Base in Florida. You can see what happened when the K index spiked up on August 5th. For that safe station, the MUF went well above 10 meters. So if you were in the right place at the right time, that's great. The geomagnetic storms are the worst of the 3 disturbances because the duration could be several days if it's a biggie, and it can be worldwide too. So, and as we approach solar maximum, geomagnetic storms, the CMEs occur mostly around, or are most prevalent around solar maximum. So we got to be on the lookout for that stuff. Solar radiation storm, when we have a big solar flare, like M5 or 6 or 7 or whatever, or an X flare, which is even bigger, relativistic protons can be accelerated. Relativistic means they're very fast, almost the speed of light, and they can funnel into the polar cap. That's the area within the auroral zone, and it causes increased absorption in the polar cap, which degrades over the pole pass. And there's a path from W5 to Russia, and it's pretty close to a W9 to Russia would go right through the auroral oval also. Those can last for a couple days, but it's only on pass through over the polar cap. So hopefully most of your paths are away from the auroral zone. And the last disturbance is radio blackouts. And if there's a big solar flare, the X-ray radiation from a big solar flare can cause increased absorption on the daylight side of the Earth, which is more loss, and the band may go away. But note that the effect diminishes as you move away from the overhead point. It goes from orange, which means the higher frequencies are affected. And the green and the blue are lower frequencies, and they're not affected as much. So there are, if there's a big solar flare and a radio blackout, generally it may last about an hour, and the thing to do is move to higher frequencies where the loss is less. Here's some references. I'll send a PDF of this presentation so people can view that and see where all the URLs are. There's some good books in there, and they're not real technical, that's for sure. So good stuff to read. So cycle 25 is still ascending. Now we might be close to solar maximum, or maybe go a bit higher. I'm rooting for a little bit higher because that'll keep 10 meters open a lot longer. Man-made noise appears to be the more critical issue than climate change on 160. And I think as we go forward, 160 meters is going to be tougher. It would be nice to get back to what happened decades ago, but I don't think so. I had a weird thought this morning about how do you cure this increased man-made noise? Well, we have a Carrington event, a big CME that causes our electrical system to go down. Then we'll be nice and quiet. Oh, well, of course, there may be a problem with that too. We had 6 meter propagation via the F2 region around cycle 24 maximum, so we should see it in cycle 25. Again, I'll just reiterate the best opportunities are during the fall and winter months and on low latitude paths. And if you're really interested in this stuff, read Jim Kennedy, K6MIO's papers at that URL. He was a physicist in Hawaii, and he wrote a lot of articles. He's retired now and lives in Florida, enjoying the grandkids and all that kind of stuff. And I can't stress it enough. Get on the high bands now, the higher HF bands, 15, 12, and 10. They're offering excellent worldwide propagation, and a modest station can do wonders. 100 watts and a simple antenna, maybe a vertical, a dipole, and inverted V. So have fun because one of these days, cycle 5 is going to start going down. Oh well, and we'll be at solar minimum again. So that's all I had. If there are any questions, I could certainly try and answer them.
Yeah, do we have questions for Carl? And Carl, you can quit sharing so that we can see everybody. There we go.
There we go. Yep.
Carl, this is Bill, W9MXQ. Just a quick question for you. When you mentioned that prop.kc2g website,
Yes.
I was
Yes.
writing another note. Is that essentially a real-time? Did you say that?
Yeah, pretty much. Once the ionosons download, he takes them and updates the map. So it's pretty doggone real time. Now you
Okay.
have to wait 15 minutes till the next update, but yeah, in 15
Well, that's
minutes.
right. You did mention the updates. Okay. Well, thank you. I appreciate that.
Yeah.
Nice presentation, by the way. A lot of thought there. I enjoyed it.
Okay, good. Gary, W9XT, did I answer your question? Kind of.
Yes, he did. Thanks very much for going into such a detailed explanation on that.
Yeah. It's an estimate, so don't, yeah. Yep. And there are probably other things happening too that there could be a short-term enhancement that we just didn't capture that caused things to improve too. So, man, who knows? A lot of stuff goes on up there with that, and we don't know about it yet, all of it yet.
Hi, it's Jim, K9YC.
Hey, Jim.
Yeah, good to see you. Always.
Yeah, you're in the wrong call area, doggone it.
Yeah, well, I sure do love it out here, though.
Yeah, I'm sure.
I strongly agree with you that of the very great importance of receive noise.
Yeah.
And the greatest thing I think that we can do to our stations is to get as far as we can into killing it.
Yep. Yeah, man-made noise. There's the possibility we can work with the power company or whatever, solar installation or something, and resolve it. And you need to do that as best as you can.
Well, the thing that I've seen, and this has become one of my areas of study, is that it's not power line noise now that dominates. It's electronic noise that dominates. Yeah. Roughly 20 some years ago, maybe earlier, in the interest of climate change and environmental issues, we mandated switch mode power supplies, but we didn't do anything to enforce the regulations that they had to be clean. And they are a very wild source. My own seat of the pants estimate is that the average home has got at least a couple of dozen of these things hooked up to the power line and generating noise. When I first moved out here at solar minima, I could work Europe sometimes. I haven't been able to on 160 on CW. I have not been able to work Europe on CW for 7 or 8 years. The difference is huge.
Yep. Yeah, I saw your comment on the top band reflector too about no beverage equals no contacts.
Well, actually, that was not my comment. Somebody else said that.
Okay.
But I was quoting Gary Shapiro, NI6T,
that's right. Yep.
Who said, any beverage is better than no beverage.
Yep. Yep. Yeah, there's no doubt that those switch mode supplies, I had 3 of them on my remote antenna switches. And I wired them up to go to a linear power supply, and that helped. But I'm sure there's other stuff in the house too.
Well, one thing I've done is over the years, I've accumulated all of the linear wall warts that I can find, and I have boxes of them and collect them from other hams and so forth. So anytime something new comes in the house, it gets one of those. Another thing that I've done, and I've done with a lot of things, is to convert stuff to float charge batteries. So if you got to put a wall wart across a battery and use the battery to drive your electronics, I'm doing that with monitors that I'm using right now to look at you. Monitors in the shack are running off my 12-volt system and so forth. So that kind of stuff, you know, we can do if we really work at it.
Yep.
Other questions for Carl? And Jim, I think many of us have read your write-ups over the years and about noise, and you know, we're enjoying good propagation and so forth, but the minimum's coming, and the stuff that you've written about is going to be very, very important in the future, but is important today. So any other questions? I'm going to stop the recording.
Okay.